Picture this. You're standing in the middle of a vast forest at midnight. The trees tower above you, their canopies so dense that you can barely see the sky. You know you're surrounded by thousands, maybe millions of trees, but you can't see the forest's edge. You can't step back and admire its full majesty because you're trapped inside it. This is exactly the predicament we've faced for centuries when trying to understand our cosmic home, the Milky Way galaxy. Every clear night, when you look up at the sky, you're seeing the inside view of one of the most spectacular structures in the universe. That faint, cloudy band of light stretching across the heavens isn't just pretty scenery, it's the edge-on view of our own galaxy, a colossal pinwheel of stars, gas, and dust that contains somewhere between 100 and 400 billion stars. And for the longest time, we had absolutely no idea how big it really was. Think about that for a moment. We can measure the distance to other galaxies millions of light years away. We can detect planets orbiting stars hundreds of light years from Earth. We can even peer back in time to see the universe when it was just a few 100 million years old. But measuring our own galaxy? That turned out to be one of the most challenging puzzles in all of astronomy. The problem is perspective. Imagine trying to measure the size of your house while you're locked inside one of the rooms. You might be able to pace out the dimensions of the room you're in, maybe even figure out the layout of adjacent rooms by listening to sounds or feeling vibrations. But determining the full extent of the house, mapping every room, every hallway, every nook and cranny, that's incredibly difficult when you can't step outside and see the whole structure. This is the challenge astronomers have faced for centuries. We're embedded deep within the Milky Way's disk, about 26,000 light-years from its center, surrounded by dust and gas that blocks our view in many directions. It's like trying to understand the layout of a massive city while standing in the middle of it during a thick fog. You can see some buildings nearby, catch glimpses of distant skyscrapers, but the full scope of the urban landscape remains hidden. But here's the remarkable thing. After decades of technological advances, ingenious observational techniques, and the combined efforts of thousands of scientists around the world, we finally have a clear picture of just how big our galactic home really is. And the answer is both more precise and more astounding than anything our ancestors could have imagined. The Milky Way, we now know, stretches approximately 100,000 to 120,000 light-years from edge to edge. To put that in perspective, light, the fastest thing in the universe, takes over 100,000 years to travel from one side of our galaxy to the other. If you could somehow travel at the speed of light, you could circle the entire Earth 7.5 times in just 1 second. But crossing our galaxy? That would take you 100,000 years of continuous travel. But the story gets even more incredible when we consider the galaxy's full extent. Recent discoveries have revealed that the Milky Way's influence extends far beyond its visible disk. We're now finding evidence of stellar streams, dark matter halos, and satellite galaxies that stretch our galaxy's reach to perhaps 200,000 light-years or more. It's like discovering that your neighborhood is actually part of a much larger community that extends far beyond what you can see from your front door. The journey to this understanding is a story of human ingenuity, technological innovation, and the relentless pursuit of knowledge. It's a tale that spans centuries, involving everyone from ancient astronomers who first noticed that strange band of light in the sky, to modern space missions that can measure stellar positions with unprecedented precision. It's a story of how we learn to see our place in the universe, not from the outside looking in, but from the inside looking out.
This breakthrough in understanding our galaxy's size isn't just an academic curiosity. Knowing the true dimensions of the Milky Way has profound implications for our understanding of how galaxies form and evolve, how many stars and planets might exist in our cosmic neighborhood, and even what might happen when our galaxy collides with its nearest large neighbor, the Andromeda Galaxy, in about 4.5 billion years. It also helps us understand our cosmic address with unprecedented precision. We live on Earth, which orbits the Sun, which is one star among hundreds of billions in the Milky Way, which is one galaxy among trillions in the observable universe. But now, for the first time in human history, we know exactly how big our galactic neighborhood really is. The story of how we figured this out is filled with brilliant insights, technological marvels, and a few surprising discoveries that changed everything we thought we knew about our galaxy. It's a journey that takes us from ancient Greek philosophers to cutting-edge space missions, from the first telescopes to artificial intelligence algorithms that can process data from billions of stars. So, how did we finally crack this cosmic mystery? How did we manage to measure something so vast from our tiny vantage point inside it? And what does this new understanding tell us about our place in the universe? The answers to these questions reveal not just the size of our galaxy, but the incredible power of human curiosity and scientific ingenuity. Long before we had telescopes, satellites, or even a basic understanding of what stars really were, humans looked up at the night sky and wondered about that mysterious band of light stretching across the heavens. Ancient civilizations around the world developed their own explanations for this celestial phenomenon, each reflecting their unique cultural perspectives and mythological traditions. The ancient Greeks called it galaxias, meaning milky, which eventually gave us our modern term galaxy. They had various explanations for its origin. Some believed it was the path souls took to reach the afterlife. Others thought it was milk spilled across the sky by the goddess Hera while nursing the infant Hercules. The Romans adopted the Greek term, calling it Via Lactea, the Milky Road, from which we get our modern name, the Milky Way. Other cultures had equally imaginative explanations. Many Native American tribes saw it as a pathway for spirits, sometimes called the Trail of Souls or the Path of Spirits. Hindu mythology described it as the celestial river Ganges flowing across the sky. Aboriginal Australian cultures often interpreted it as a great emu or other animals stretched across the heavens. Norse mythology portrayed it as the path to Valhalla, where fallen warriors would journey after death.
These mythological explanations, while beautiful and culturally significant, were humanity's first attempts to make sense of what we now know is our view from inside one of the universe's most magnificent structures. But it would take thousands of years and revolutionary advances in our understanding of the cosmos before we could begin to grasp the true nature of what we were seeing. The first major breakthrough came in 1610, when Galileo Galilei pointed his primitive telescope at the Milky Way. What he saw astonished him and changed our understanding forever. That smooth, cloudy band of light wasn't a mysterious cosmic river or celestial pathway. It was composed of countless individual stars, so numerous and distant that they blended together into a continuous glow when viewed with the naked eye. Galileo's discovery was revolutionary, but it raised as many questions as it answered. If the Milky Way was made of stars, how many stars were there? How far away were they? And most puzzling of all, why did they appear to form this distinctive band across the sky rather than being scattered uniformly in all directions? The next crucial insight came from the brilliant German-British astronomer William Herschel in the late 18th century. Herschel, along with his sister Caroline, conducted the first systematic attempt to map the structure of what we now call our galaxy. Using powerful telescopes of his own design, Herschel counted stars in different regions of the sky, attempting to understand the three-dimensional structure of the stellar system that contained our sun. Herschel's method was ingenious in its simplicity. He reasoned that if he counted more stars when looking in one direction than another, it meant that the stellar system extended further in that direction. By systematically counting stars across the entire sky, he hoped to map out the shape and size of our cosmic neighborhood. His results suggested that we lived in a flattened, disc-like structure with the sun near its center. This explained why we saw the Milky Way as a band around the sky. We were looking through the thin dimension of the disk when we looked up or down, seeing relatively few stars. But when we looked along the plane of the disk, we saw through its full thickness, resulting in the dense concentration of stars we observe as the Milky Way band. Herschel's estimate was that this stellar system was about 5 times wider than it was thick, and he calculated its extent to be roughly 1,000 times the distance to the bright star Sirius. While his specific measurements were far from accurate by modern standards, his fundamental insight about the disk-like structure of our stellar system was remarkably prescient. However, Herschel made one crucial error in his reasoning.
He assumed that we could see all the stars in our galaxy, that there was nothing blocking our view to the galaxy's edge. We now know this assumption was wrong. The space between stars isn't empty. It's filled with gas and dust that absorbs and scatters starlight, limiting how far we can see invisible light. This cosmic fog meant that Herschel's star counts were telling him more about the local distribution of dust than the true extent of the galaxy. The next major advance came in the early 20th century from the American astronomer Harlow Shapley. Shapley was studying globular clusters, dense spherical collections of hundreds of thousands of ancient stars that orbit our galaxy like distant satellites. By carefully measuring the distances to these clusters, Shapley made a startling discovery. They weren't distributed randomly around the sky. Instead, they formed a roughly spherical halo centered on a point in the constellation Sagittarius, far from our location in the galaxy. Shapley realized that this distribution pattern revealed something profound about our place in the galaxy. The globular clusters were orbiting the true center of our stellar system, and that center was located about 26,000 light-years away in the direction of Sagittarius. This meant that our sun, far from being at the center of the galaxy as Herschel had assumed, was actually located in the galactic suburbs, about halfway out from the center to the edge. This discovery was as revolutionary as Copernicus's realization that Earth wasn't the center of the universe. Just as Earth was demoted from the center of the universe to merely one planet among many orbiting the sun, our sun was now revealed to be just one star among billions in a vast system located far from that system's center. Shapley also provided the first reasonable estimate of the galaxy's true size. Based on his measurements of globular cluster distances, he calculated that our galaxy was roughly 100,000 light-years in diameter, an estimate that, remarkably, remains close to our best modern measurements.
But perhaps the most revolutionary discovery was yet to come. In the 1920s, Edwin Hubble, using the powerful new 100-inch telescope at Mount Wilson Observatory, was studying what were then called spiral nebulae, fuzzy, spiral-shaped patches of light scattered across the sky. Many astronomers thought these were nearby clouds of gas and dust within our own galaxy, perhaps forming new solar systems. Hubble made a discovery that changed everything. By carefully observing variable stars in these spiral nebulae, he was able to measure their distances. What he found was shocking. These nebulae were incredibly far away, so far that they couldn't possibly be part of our own galaxy. They were separate galaxies entirely, each containing billions of stars, scattered throughout a universe far larger than anyone had imagined. This discovery revealed that our Milky Way galaxy was just one of countless galaxies in the universe. The cosmos wasn't a single vast system of stars, with our sun somewhere within it. Instead, it was a universe filled with separate island universes, each a massive collection of stars, gas, and dust, separated by enormous voids of nearly empty space. Hubble's discovery put the final pieces in place for our modern understanding of the Milky Way's place in the cosmos. We now knew that we lived in a disk-shaped galaxy, roughly 100,000 light-years across, with our sun located about 26,000 light-years from the center. This galaxy contained hundreds of billions of stars and was just one of countless similar structures scattered throughout the universe. However, even with these fundamental insights, many questions remained. How massive was our galaxy? How many stars did it contain? What was its exact structure? And most challenging of all, what were its precise dimensions? These questions would drive astronomical research for decades to come, leading to increasingly sophisticated observational techniques and, eventually, to the space-age technologies that would finally give us definitive answers about the true size of our galactic home. The story of our evolving understanding of the Milky Way is a testament to human curiosity and ingenuity. From ancient myths to telescopic observations, from star counts to distance measurements, each generation of astronomers built upon the work of their predecessors, gradually piecing together a more complete and accurate picture of our cosmic neighborhood. But as we'll see, the challenge of measuring the galaxy's true size from our location within it would prove to be one of the most difficult problems in all of astronomy.
Imagine you're an ant living inside a vast library tasked with measuring the building's dimensions. You can crawl around the floor you're on, maybe climb up or down a few levels, but you can't fly above the building to see its full extent. You can't even see very far in any direction because towering bookshelves block your view. Some sections are brightly lit, others are shrouded in shadow. And to make matters worse, you can't tell the difference between a nearby small bookshelf and a distant tall one without somehow measuring the distance to each one. This analogy captures the essence of why measuring the Milky Way has been such a monumental challenge for astronomers. We're not external observers looking at our galaxy from a comfortable distance. We're embedded deep within it, surrounded by the very structures we're trying to measure, with our view obscured by cosmic dust and our perspective limited by our location. The first and most fundamental problem is our position within the galactic disk. The Milky Way is a spiral galaxy, meaning it has a relatively flat, disk-like structure with spiral arms winding outward from a central bulge. Our solar system is located within this disk, roughly halfway between the center and the edge, and about 25 light-years above the galactic midplane. This means that when we look in the direction of the galactic plane, which appears as the Milky Way band in our night sky, we're looking through the full thickness of the disk. When we look perpendicular to this plane, up or down from the galactic disk, we quickly run out of galaxy to observe. This geometry creates what astronomers call the zone of avoidance. In the direction of the galactic center, our view is so severely obscured by dust and stars that we can barely see beyond our local neighborhood. It's like trying to see across a crowded stadium from field level during a thick fog. You might be able to make out some nearby spectators, but the far side of the stadium is completely hidden from view. The second major challenge is interstellar dust. The space between stars isn't empty. It's filled with tiny particles of dust, mostly carbon and silicon compounds, that absorb and scatter starlight. This cosmic dust is particularly effective at blocking shorter wavelengths of light, which is why distant stars often appear redder than they actually are. The dust doesn't just dim the light from distant objects, it can completely obscure them. To understand the impact of this dust, consider that visible light can typically travel only about 1,000 to 3,000 light-years through the galactic disk before being completely absorbed. Given that our galaxy is over 100,000 light-years across, this means we can see less than 5% of the way to the galaxy's edge in visible light alone. It's as if we're trying to map a city while wearing sunglasses so dark that we can only see a few blocks in any direction. The third challenge is the sheer scale involved. Even light, traveling at 186,000 miles per second, takes over 100,000 years to cross our galaxy. The distances involved are so vast that they strain our ability to measure them accurately. Traditional methods of distance measurement, such as parallax, which relies on observing how nearby stars appear to shift position as Earth orbits the Sun, only work reliably for stars within a few hundred light-years of Earth.
Parallax is like using your depth perception to judge distances. Close one eye, then the other, and nearby objects appear to shift position relative to the background. The closer the object, the larger the apparent shift. But try this with a mountain on the horizon, and you'll notice the shift is so small, it's barely perceptible. For very distant mountains, there's no detectable shift at all. Similarly, for stars more than a few thousand light-years away, the parallax shift is so tiny that it becomes impossible to measure accurately with ground-based telescopes. The fourth challenge is understanding the galaxy's structure. The Milky Way isn't a simple disk with clearly defined edges. It has a complex, multi-component structure that includes the central bulge, the thin disk where most stars reside, a thick disk of older stars, and an extended halo of dark matter and sparse stellar populations. Each component has different properties and extends to different distances from the galactic center.
Moreover, the galaxy's spiral arms create density variations throughout the disk. Some regions have many more stars than others, and these variations can fool us into thinking we're seeing the galaxy's edge when we're actually just looking through a region with fewer stars. It's like trying to determine the size of a forest by looking at tree density, not realizing that some areas are naturally more sparse than others. The fifth challenge is distinguishing between objects that belong to our galaxy and those that don't. The space around the Milky Way isn't empty. It contains satellite galaxies, stellar streams from disrupted smaller galaxies, and various other structures. Determining whether a particular group of stars is part of the Milky Way's outer halo or a separate nearby galaxy requires careful analysis of their motions and compositions. Additionally, there's the problem of defining what we mean by the edge of the galaxy. Unlike a planet or a star, galaxies don't have sharp boundaries. The density of stars gradually decreases as you move away from the galactic center, but there's no clear point where the galaxy definitively ends and intergalactic space begins. It's like trying to define the edge of a city. Do you count the dense urban core, the suburbs, or the scattered rural communities that might still be considered part of the metropolitan area? The sixth major challenge is the galaxy's motion and rotation. The Milky Way isn't static. It's rotating with different parts moving at different speeds. Stars closer to the center complete their orbits faster than those farther out, creating a complex pattern of motions that must be accounted for when trying to map the galaxy's structure. Additionally, the entire galaxy is moving through space, interacting gravitationally with nearby galaxies and galaxy clusters. These motions mean that measuring the galaxy requires understanding not just where objects are, but how they're moving. This adds another layer of complexity to an already challenging problem. It's like trying to map a city where all the buildings are constantly moving in different directions at different speeds. The seventh challenge is technological limitation. For most of human history, we've been limited to observing the universe in visible light, and even then, only with ground-based telescopes that had to peer through Earth's turbulent atmosphere. This atmosphere distorts and blurs the light from stars, limiting the precision of measurements. Weather, light pollution, and atmospheric conditions all affect observations, making consistent, high-precision measurements extremely difficult.
Finally, there's the challenge of data interpretation. Even when we can make accurate measurements of star positions and motions, interpreting this data to understand the galaxy's structure requires sophisticated theoretical models. We need to understand how galaxies form and evolve, how dark matter affects their structure, and how various stellar populations are distributed throughout the galaxy. Each of these challenges would be formidable on its own, but together they created a nearly insurmountable obstacle to understanding our galaxy's true size and structure. For centuries, astronomers made progress by developing clever workarounds and increasingly sophisticated techniques, but fundamental limitations in observational capability meant that many questions about the Milky Way remained unanswered. It would take revolutionary advances in technology, space-based observatories that could observe from above Earth's atmosphere, detectors sensitive to wavelengths of light that aren't walked by interstellar dust, and computational techniques that could process vast amounts of data to finally overcome these challenges. The story of how astronomers developed these tools and used them to finally measure our galaxy is a testament to human ingenuity and persistence in the face of seemingly impossible obstacles. The breakthrough in understanding the Milky Way's true size didn't come from a single observation or discovery. Instead, it emerged from a convergence of revolutionary technologies developed over the past several decades, each addressing different aspects of the measurement challenge. Like assembling a cosmic jigsaw puzzle, astronomers needed multiple tools working in concert to finally see the complete picture of our galaxy. The Gaia revolution, precision beyond imagination. The most transformative of these tools is the European Space Agency's Gaia mission, a space-based observatory that has revolutionized our understanding of the Milky Way.
Launched in 2013, Gaia represents the culmination of decades of technological development and represents perhaps the most ambitious stellar mapping project ever attempted. Gaia's mission is elegantly simple in concept, but staggeringly complex in execution. To measure the precise positions, distances, and motions of over 1 billion stars in our galaxy. To appreciate the magnitude of this achievement, consider that Gaia can measure stellar positions with an accuracy of 10 microarcseconds, roughly equivalent to measuring the width of a human hair from a distance of 1,000 kilometers away. The spacecraft accomplishes this remarkable precision through several ingenious design features. First, it operates from the position called L2, about 1.5 million kilometers from Earth in the direction away from the Sun. This location provides a stable, interference-free environment where Gaia can continuously observe the sky without obstruction from Earth or the Moon. Gaia carries 2 telescopes that simultaneously observe different regions of the sky. As the spacecraft slowly rotates, these telescopes sweep across the entire sky every 6 months, repeatedly observing each star multiple times. This repetition is crucial because it allows Gaia to detect the tiny shifts in stellar positions caused by parallax, the apparent movement of nearby stars against the more distant stellar background as Earth and Gaia orbit the Sun. But Gaia doesn't just measure positions, it also records each star's brightness in multiple colors, providing information about stellar temperature, composition, and evolutionary stage. Most importantly, by comparing observations taken months apart, Gaia can measure the proper motion of stars, their movement across the sky over time. This information is crucial for understanding the galaxy's rotation and structure. The data processing requirements for Gaia are mind-boggling. The spacecraft generates about 50 gigabytes of data per day, and by the end of its mission, it will have made over 1,000 billion measurements of stars and other celestial objects. Processing this information requires some of the world's most sophisticated data analysis techniques, including machine learning algorithms that can identify patterns in the data that would be impossible for humans to detect. Radio astronomy, seeing through the dust. While Gaia provides unprecedented precision for near-Earth stars, radio astronomy has been crucial for mapping the more distant regions of our galaxy. Radio waves have a key advantage over visible light. They pass through interstellar dust almost unimpeded. This means radio telescopes can see all the way to the far side of the galaxy and beyond, regions that are completely invisible to optical telescopes. One of the most important radio astronomy techniques for studying galactic structure involves observing the radio emission from hydrogen gas. Hydrogen is the most abundant element in the universe, and under certain conditions, hydrogen atoms emit radio waves at a very specific frequency, 1420.4 megahertz, corresponding to a wavelength of 21 centimeters. This 21 centimeter line has been a goldmine for galactic astronomy. By observing this emission from different directions and measuring its Doppler shift, the change in frequency caused by the motion of the gas, astronomers can map not only where hydrogen gas is located throughout the galaxy, but also how fast it's moving. This information has been crucial for understanding the galaxy's rotation curve and spiral structure. Radio astronomy has also revealed the existence of the galaxy's stellar halo through observations of RR Lyrae stars and other stellar populations that can be detected at radio wavelengths. These ancient metal-poor stars provide important clues about the galaxy's formation and early evolution. Pulsar timing, nature's most precise clocks. Pulsars, rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses, have provided another crucial tool for mapping the galaxy. These exotic objects are the ultra-dense remnants of massive stars that have exploded as supernova, containing as much mass as our Sun, compressed into a sphere only about 20 kilometers across.
Many pulsars rotate with incredible regularity, emitting pulses of radio waves that arrive at Earth with the precision of atomic clocks. By carefully timing these pulses over months and years, astronomers can detect tiny changes in the arrival times that reveal information about the pulsar's motion through space and the gravitational fields it encounters. This technique, known as pulsar timing, has been instrumental in mapping the galaxy's gravitational field and understanding the distribution of matter throughout the galactic disk and halo. Pulsars act like test particles moving through the galaxy's gravitational field, and by tracking their motions precisely, astronomers can infer the underlying mass distribution. Pulsars have also provided crucial information about the galaxy's magnetic field structure. As pulsar signals travel through the galaxy's magnetized plasma, they undergo a process called Faraday rotation that changes the polarization of the radio waves. By measuring this effect for pulsars at different distances and locations, astronomers can map the galaxy's magnetic field in 3 dimensions. Very long baseline interferometry, the ultimate resolution. For the most precise measurements of stellar positions and motions, astronomers have developed a technique called Very Long Baseline Interferometry, or VLBI. This technique combines signals from radio telescopes separated by thousands of kilometers, creating a virtual telescope with the resolution of a single instrument as large as the separation between the telescopes. VLBI can achieve angular resolutions of less than a milli-arcsecond, precise enough to read a newspaper on the moon from Earth. This extraordinary precision has made it possible to measure the proper motions of stars and other objects with unprecedented accuracy, providing crucial data for understanding galactic structure and dynamics. One of VLBI's most important contributions to galactic astronomy has been the precise measurement of the distance to the galactic center. By observing the radio emission from gas clouds orbiting the supermassive black hole at the galaxy's center, and combining this with measurements of their orbital velocities, astronomers have determined that the galactic center is 26,673 light-years away, with an uncertainty of only about 600 light-years. Stellar surveys, cataloging the galaxy. Beyond these high-precision techniques, astronomers have conducted numerous large-scale surveys to catalog and characterize stars throughout the galaxy. Projects like the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and the upcoming Vera Rubin Observatory have observed millions of stars, providing statistical information about stellar populations, ages, and chemical compositions. These surveys have revealed the complex structure of the galactic halo, identifying stellar streams, the disrupted remains of small galaxies that have been torn apart by the Milky Way's gravity. By tracing these streams, astronomers can map the outer reaches of our galaxy and understand how it has grown over time through the accretion of smaller systems. Infrared surveys have been particularly valuable because infrared light can penetrate dust more effectively than visible light, allowing observations deeper into the galactic plane. The Spitzer Space Telescope and other infrared observatories have mapped the galaxy's spiral structure and identified previously unknown stellar populations. Computational astrophysics, modeling the galaxy. Modern computational techniques have been equally important in interpreting observational data. Sophisticated computer simulations can model how galaxies form and evolve over billions of years, providing theoretical frameworks for understanding observations. These simulations incorporate our understanding of dark matter, gas dynamics, star formation, and stellar evolution to create detailed models of galactic structure. By comparing these models with observations, astronomers can test their theories and refine their understanding of how galaxies work. Machine learning techniques have become increasingly important for processing the vast data sets produced by modern astronomical surveys. These algorithms can identify patterns in data that would be impossible for humans to detect, classify different types of stars and stellar systems automatically, and even discover new types of astronomical objects. Dark matter detection, the invisible component.
Understanding the galaxy's size also requires accounting for dark matter, the mysterious substance that makes up about 85% of all matter in the universe, but interacts only through gravity. While we can't see dark matter directly, its gravitational effects on visible matter provide clues about the galaxy's total mass and structure.
Direct dark matter detection experiments, while not yet successful in identifying dark matter particles, have provided important constraints on dark matter properties that inform theoretical models of galactic structure. Indirect detection techniques, looking for the products of dark matter annihilation, have also contributed to our understanding of how dark matter is distributed throughout the galaxy. The combination of all these techniques, space-based astrometry, radio astronomy, pulsar timing, VLBI, stellar surveys, computational modeling, and dark matter studies, has finally provided astronomers with the tools needed to measure the Milky Way's true dimensions and structure. Each technique addresses different aspects of the measurement challenge, and together they paint a comprehensive picture of our galactic home. The technological revolution that made these measurements possible represents one of the greatest achievements in the history of astronomy. From the precision engineering of space-based observatories to the sophisticated algorithms needed to process astronomical big data, the effort to understand our galaxy has driven innovations that benefit not just astronomy, but many other fields of science and technology. After centuries of speculation and decades of increasingly sophisticated measurements, we finally have a remarkably detailed picture of our galaxy's true dimensions. The answer turns out to be both more precise and more complex than early astronomers ever imagined. The Milky Way isn't simply a disk with a clearly defined edge, it's a multi-layered dynamic structure, with components extending far beyond what we can see with our naked eyes. The galactic disk, our stellar neighborhood. Let's start with the most familiar component, the galactic disk, where our sun and most of the stars we see in the night sky reside. Based on the latest data from Gaia and other observatories, the visible stellar disk of the Milky Way extends approximately 100,000 to 120,000 light-years from edge to edge. This measurement represents the diameter of the region containing most of the galaxy's ordinary matter, stars, gas, and dust. To put this scale in perspective, imagine shrinking the entire galaxy down so that Earth's orbit around the Sun, about 186 million miles across, becomes the size of a quarter. On this scale, the galactic disk would be about 26 kilometers in diameter. Our Sun would be located roughly 7 kilometers from the center in what astronomers might consider the galactic suburbs. The disk itself has a complex, layered structure. The thin disk, where most star formation occurs today, has a thickness of only about 2,000 light-years, remarkably thin compared to its diameter. If our quarter-sized galaxy model were accurate, this thin disk would be only about half a millimeter thick, thinner than a sheet of paper. Above and below this thin disk lies the thick disk, containing older stars that formed when our galaxy was younger and more turbulent. This thick disk extends roughly 6,000 to 8,000 light-years above and below the galactic plane, giving the overall disk structure a total thickness of about 12,000 to 16,000 light-years. Recent observations have also confirmed that the galactic disk isn't perfectly flat. Like a vinyl record that's been slightly warped, the outer regions of the disk show a distinct twist and flare. This warping becomes more pronounced toward the galaxy's edge, with some regions extending up to 15,000 light-years above or below the average galactic plane. The central bulge, ancient heart of the galaxy.
At the galaxy's center lies the bulge, a roughly spherical collection of old, metal-rich stars that formed early in the galaxy's history. This central bulge extends about 10,000 light-years from the galactic center and contains some of the oldest stars in the Milky Way, many over 10 billion years old. Recent studies have revealed that this bulge has a complex peanut-like or bar-like shape when viewed from certain angles. This structure, formed by gravitational instabilities in the galaxy's early history, extends roughly 27,000 light-years from end to end. The bar's influence on galactic structure extends well beyond the bulge itself, affecting the motion of stars and gas throughout much of the inner galaxy. At the very center of this bulge lurks Sagittarius A star, a supermassive black hole containing about 4.1 million times the mass of our Sun. While the black hole itself is tiny compared to galactic scales, its event horizon is only about 24 million kilometers across. Its gravitational influence affects the motion of stars within several light-years of the galactic center. the stellar halo, ghosts of ancient mergers. Beyond the galactic disk lies one of the most fascinating and difficult to study components of our galaxy, the stellar halo. This roughly spherical distribution of old, metal-poor stars extends far beyond the visible disk, containing the fossil remains of smaller galaxies that merged with the Milky Way billions of years ago. The stellar halo is incredibly sparse compared to the disk. If the galactic disk is like a bustling city, the halo is like a vast countryside with only scattered farmhouses. The average distance between stars in the halo can be hundreds of light years, compared to just a few light years in the galactic disk near the Sun. Recent discoveries have revealed that this halo extends much farther than previously thought. Gaia data and other observations have identified halo stars at distances of 300,000 light years from the galactic center, nearly 3 times the diameter of the stellar disk. Some studies suggest that the most distant halo stars may extend even farther, possibly reaching 500,000 light years or more from the galactic center. Within this halo, astronomers have identified numerous stellar streams, long, thin trails of stars that represent the disrupted remains of smaller galaxies and globular clusters. These streams provide a fossil record of the Milky Way's growth through cosmic cannibalism, showing how our galaxy has consumed dozens